The Turing Test, developed by Alan Turing in 1950, is a key benchmark for assessing machine intelligence. It measures a machine's ability to simulate human-like conversation, using a text-only interface for impartial evaluation. Alan Turing was a British mathematician, computer scientist, and World War II codebreaker. He pioneered artificial intelligence and computing theory, introducing key concepts about machine thinking and reasoning. Turing initially called the test the imitation game. It involves a judge attempting to distinguish between a human and a machine, focusing strictly on conversation and responses, not physical appearance or voice. The test structure involves 3 participants: a judge, a human, and a machine. The judge interacts via a keyboard without visual or audio clues. The machine's objective is to convince the judge that it is human. Turing shifted the philosophical question from, can machines think, to, can machines behave indistinguishably from humans? This focuses on observable behavior rather than internal conscious states. Turing's landmark 1950 paper, Computing Machinery and Intelligence, established the test's blueprint. It sparked debates on what constitutes thinking, and provided a framework for modern AI research. In the imitation game, the judge interacts blindly, asking any suitable questions. Both the human and the machine reply, their identities hidden. Success means the judge cannot reliably differentiate between them. A machine passes the test if it fools the judge at least 30% of the time across several sessions. The assessment emphasizes conversational plausibility and coherence, not merely providing correct answers. Passing the test requires key capabilities, including natural language processing, knowledge representation, learning and adaptation, and reasoning, often including intentional errors to seem more human. An early example is ELIZA, created in 1966. It simulated a psychotherapist using pattern matching, demonstrating basic conversational AI but lacking true understanding, highlighting the limits of rule-based systems. The Loebner Prize is an annual contest since 1990 for conversational AI bots. Judges assess the bot's human likeness. However, the prize is often criticized for focusing too heavily on deception. Eugene Goostman, simulating a 13-year-old boy, claimed to pass the test in 2014 with 33% success. This achievement sparked debate due to the limited nature of open-ended conversation used in the trial. A major criticism is that the test measures only imitation, not genuine understanding. Machines can pass by manipulating judges, and the test ignores other forms of intelligence, like physical reasoning or emotion. Philosophical debates continue, such as John Searle's argument that passing the test doesn't equate to possessing a mind. The core debate remains simulation versus genuine cognition. The test has variations, including the visual Turing test for human-like visual perception. The total Turing test extends this to image recognition, movement, and sensory processing via multimodal interactions. Limitations of the test include the need for a controlled environment and its reliance on conversational context, which may overlook broader intelligence. It also adapts slowly to fast-paced AI technology advances. Modern AI benchmarks now focus on specific cognitive skills like vision, robotics, and common sense reasoning. While AI seeks broader assessments, the Turing test remains a significant reference point. The Turing test's significance lies in setting the stage for research in NLP, machine learning, and knowledge representation. It reoriented the focus of AI to interaction, inspiring generations of researchers. In popular culture, the Turing test popularized AI and shaped society's expectations and fears of machine minds. It is frequently referenced in discussions about robot rights and consciousness. Future tests will likely evaluate AI in vision, robotics, and multimodal dialogue. The Turing test continues to provoke inquiry into what truly defines intelligence and whether machines can possess consciousness. Intelligent agents are autonomous entities central to AI that perceive their environment and act to achieve set goals. They can be software programs, robots, or complex multi-agent systems. Key characteristics of intelligent agents include autonomy, allowing operation without human intervention. Agents use sensors for perception and actuators or effectors to take action and influence the environment. Rational agents strive for the best possible outcome using available knowledge. Their performance is defined by a measurable objective, and their rationality is based on information and prior experience. Types of intelligent agents range from simple reflex agents, acting only on current perception, to utility-based agents, which weigh actions based on expected utility, and goal-based agents that use goals to guide their actions. Agents interface with the environment by perceiving data via sensors and acting with effectors. This creates an ongoing loop: perceive, decide, act, and perceive again. Actions are designed to maximize an objective function or goal, which can be predefined or learned. For instance, a learning agent optimizes a reward function in reinforcement learning. Intelligent agents use machine learning methods to adapt and improve performance over time using experience. Memory and past outcomes are crucial factors influencing future actions. Agents use algorithms, planning, reasoning, and heuristic methods to decide on actions that maximize expected outcomes. Advanced agents often leverage probabilistic and optimization techniques. Software agents, like chatbots and virtual assistants, act digitally. Physical agents, or robots, perceive real-world data and perform tangible actions. Both follow the core agent paradigm. Multi-agent systems involve multiple interacting agents, which can be cooperative or competitive. Examples include swarm robotics. These systems require mechanisms for coordination, communication, and negotiation. Agent architectures include rule-based, layered, hybrid, and the belief-desire-intention model. The choice of architecture depends on the complexity of the environment and the required functionality. The BDI model emphasizes beliefs, which is environment knowledge, desires or objectives, and intentions, which are the actions to be performed. This allows for flexible decision-making in dynamic environments. Agent intelligence ranges from basic rule following to advanced learning and autonomous reasoning. Modern agents often combine multiple levels, including context memory and social skills. Real-world applications of intelligent agents are widespread, including autonomous vehicles, smart home systems, fraud detection bots, and virtual assistants like Siri and Alexa. Intelligent agents offer advantages such as automating complex tasks with minimal human supervision. They provide scalability, speed, efficiency, adaptability, and reduced errors. Challenges in agent design include managing environmental uncertainty and incomplete information. It's crucial to ensure robust adaptation, avoid unintended consequences, and address ethical concerns. Governance and ethics require the alignment of agent objectives with human values. Ongoing concerns include autonomy, bias, privacy, and accountability, demanding continuous oversight and risk assessment. Intelligent agents are foundational in defining and measuring AI progress, bridging algorithms with real-world actions. They emphasize measurable, observable behaviors over purely philosophical concepts. The future of intelligent agents involves a movement toward more proactive, collaborative, and general-purpose systems. These agents will operate in unpredictable environments by combining deep learning and symbolic reasoning. Intelligent agents enable powerful automation and decision-making across various domains. Open questions remain on how to make agents safer, more explainable, and achieve greater general intelligence.
Rationality is the core principle of making decisions or taking actions that maximize goals based on available information. It is central to fields like philosophy, psychology, and artificial intelligence. In AI, rationality means an agent acts to maximize its performance based on what it knows and can do. A rational agent selects the action with the highest expected utility. An agent is defined as rational if it consistently performs the right action to maximize its specified performance measure. Decisions are fundamentally based on knowledge, percepts, and potential actions. AI features two main types of rationality: perfect rationality, which assumes unlimited resources and information, and bounded rationality, which seeks a good enough solution given constraints.